So hello and good morning, everyone. It is 9 o'clock in Austria, 10 o'clock in Finland, and I welcome you back to our online lecture series, Sustainable Development Approaches in Engineering Research and Education, where we want to connect you with leading experts, share insights into new discoveries, and connect you to a global platform. My name is Anna Wojka, and I'm your guide through these lectures. So I am inviting you to join me on a journey to the beautiful north, to Finland, where we are going to the Finnish branch of our Center for Mining Education under the auspices of UNESCO. There, we are meeting docent Dr. Sami Virolainen, who is already waiting for us and still enjoying some coffee, but you still have 1 or 2 more minutes. So yeah, Dr. Sami Virolainen is leader of a research team at Lappeenranta University of Technology. Jointly with his team, they are working on the recovery of valuable metals from secondary raw materials by using hydrometallurgical separation methods. He further is the director of a multidisciplinary research platform, which is called Sustainable Circularity of Inorganic Materials. In his lecture, he will draw our attention to the huge societal challenge in Europe to balance supply and demand of certain raw materials. He will share with us the significance of recovering these raw materials from secondary sources to attack the supply risk by emphasizing hydrometallurgical separation methods. So please join me by welcoming Dr. Sami Virolainen.
Thank you very much for the kind introduction, Anna, and good morning to all, also from sunny Finland. And welcome to the lecture. Yes, Anna already introduced, the topic will be today a circularity of critical metals. And just first, very briefly, few words about where I come from and who I am. Anna already made a quite good introduction, but I'll still raise some points here. So. The Lappeenranta University of Technology used to go under the name of Lappeenranta University of Technology, but now we have another main campus and then a few more regional campuses around the southeastern Finland. The main campus Lappeenranta is located just by the Russian border, like 250 kilometers from Helsinki to east. We are a small university having around 5,000 undergraduate students, around 1,000 employees, and around a couple of hundreds of PhD students. It's established in the late 60s when the political decisions were done in Finland to distribute small universities around the country regionally. And we are one of them, and now currently like having a quite strong cooperation and growth regionally also to another cities and towns close by. Okay, then again shortly about me. So as Anna mentioned, I'm a leader of a small research team for industrial hydrometallurgy. We are currently having 4 PhD students, and in addition, varying amounts of master's students and laboratory assistants and summer trainees, depending on the season. But yeah, we are doing industrial hydrometallurgy, but mostly also concentrating on the so-called selective chemical separation methods, meaning mainly liquid extraction and ion exchange. So we may do leaching sometimes if needed. We have facilities and knowledge on that. We may do precipitations also, but they are not in our core focus, but the chemical separation methods are. Then I'm teaching the issues in our bachelor's and master's level, and obviously then the PhD students. And then as Anna mentioned, since beginning of this year, I've been a director of this multidisciplinary platform for sustainable circularity of inorganic materials. So we at LUT, we have 5 of these platforms. They are all multidisciplinary and concentrated to some important societal topic or technological problem, and this platform is then related to the inorganic material circularity, from which obviously metals are then very important part. But yeah, I don't want to advertise this anymore, but this is a fresh thing. So on last Friday we had a small seminar of 2 hours called launch event of this platform, and the recording is available. So when I share you these slides after this lecture, you can find the link to the whole event, and especially if you are interested on the topic, the keynote lecture and especially the panel discussion is very fruitful there. So there are 4 experts from Finland and Sweden, mainly from battery metal sector, but also in general about metals recycling things discussing there. Okay, the first subtopic will be a discussion on the societal background of the circularity of critical metals. And probably some of you have seen this report and map before, but what I'm trying to discuss in this slide is the importance of recycling and circularity to raw materials and critical raw materials and metals to the Europe. So since 2011, it was the first time when EU made this critical raw materials list. It didn't contain 30 raw materials as it does nowadays, a little bit less, but like over 15 still. Anyways, the motivation was that it was detected that we are having a high supply risk for some important raw materials in Europe. So the definition for the critical raw materials is based on the supply risk and the economical importance. So when they both are high enough, the raw material rises to the list. And this map here wants to show in the down left, it wants to highlight the fact that Europe and continental Europe, EU area is, if we exclude Russia, it's a fairly small continent geographically. And then, like obviously, the metals and minerals are not statistically distributed and evenly. So the Earth's crust is not homogeneous in nature, but anyways, when we look at the size of the Europe, it's natural conclusion that we don't have a huge reserves, huge mineral resources in our continent, and this is the case in reality. So here the green countries represent the ones that have a significant resources for these critical raw materials, but this applies in general for minerals. So the big players are elsewhere in Latin America, USA, Russia and China are very strong, and Australia. And this has now led to the fact that when our society has been turning to more and more to a high technology devices, and many of our daily activities also rely on these high technology products. It means that the products need quite much metals, and they are some minor metals also that are not so abundant, and many metals are needed, and that has led to the supply risk. So it is just so that not all of the new equipment that we come up with, there are not enough of these critical metals for them. And this is now the story behind this list of critical raw materials for Europe. And here in the bottom right, where the list is, I have highlighted the metals as red font. So some of the critical raw materials are industrial minerals, but most of them are metals. And the bold ones here are the new ones in the list compared to the 2017. And there the interesting thing is the hot topic of lithium. So it has been under the discussion in 2017, already in 2014 a little bit, and perhaps it has gained almost most attention of these metals, but this is the first time that it is in the list. Rare earths are a very hot topic also, but lithium and battery metals are very hot topics. But we need to be aware that, for example, the lithium, there are quite a lot of primary resources around the world. The fact is just that there is quite a lot of uncertainty when the growth of use of these battery metals is really strong when we are moving towards electric mobility. And now the lithium has been typically somewhere here, so nearby the critical region, but not yet made to it until now, 2020. So it has shifted here just about there. Okay, but this is in EU. We need to be aware that in addition, there are definitions of critical raw materials in big countries. They are own definitions or own lists. Obviously similar background, so economic importance and the supply risk are the factors. Here is one researcher who has made a list of for the whole periodical table of elements and how critical they are. Yeah, so Mike Pitts concludes that really it is about the high-tech gadgets that we are using quite a lot of, and with increasing rate, and it creates the supply risk for some critical metals. But this is a good quote down here also, is that although recycling of metals and recycling them from waste electronics, for example, has gained a lot of attention lately in the past years, but still the recycling rates are not very high, and still quite a lot of the scrap and waste that contain significant amounts of metals are exported as scrap and waste from Europe, for example. You may have seen some documentaries about it also. So it's not even very legal, or at least in a gray area where containers are loaded with the scrap devices and shipped from Europe to Asia or Africa. Okay, well, this might be obvious, but still worth of noting about the terminology. So we need to understand that critical metals doesn't equal to valuable metals or the price of the metals. So obviously the criticality and the supply risk and demand affect to the metals prices. That's a law of market economy. But anyways, here, for example, I have listed some metal prices. So the red ones are in the critical raw materials list. So they may be some tens of US dollars per kilogram, like cobalt. There has been a lot of variation due to the battery, electric vehicle battery and lithium ion battery boom. So there are variations, but anyways, the critical metals and raw materials their price can vary, like from a couple of dollars. Magnesium is not even that value or expensive, and up to, for example, indium of a little bit over $1,000. And it's also noteworthy that some of the most expensive metals, like rhodium and gold, here are tens or even hundreds of dollars per kilogram. They are not labeled as critical. Well, I observed from the chat, perhaps it was the purpose for Anna to ask the questions, but I observed that somebody asked that shouldn't the need for a cobalt increase its price? Yeah, it should. That's how it goes. So actually, the price peak was somewhere around 2018. So it rised quite quickly within a couple of months to almost $100. So now it has been leveling off a little bit. So there is a little bit more supply certainty and so on. But you need to also be aware that the raw material markets are complicated, and the prices mechanism for formation of the prices, obviously, like the basic rules of supply and demand, and their balance is there, but it's really complicated, and the minor metals typically have a very large fluctuation. If so, for example, some new use is established, or like a temporarily there is some large use for some minor metal for a while, it may increase the price like 2 or 10-fold. For example, a good example was like around 15 years ago, the metal called Rhenium. It's a minor metal. Typically the price is around, let's say, $1,000 or $2,000 a kilogram. But when United States Air Force launched a large aircraft, like a program where they build a lot of new aircrafts, and the rhenium is used in the alloys of the engine turbines. So in that case, they needed a lot of rhenium, and the price increased like to $11,000 a kilogram for a while. But what I was about to mention about the prices also is that, for example, the base metals, they are in the stock markets, and one thing to understand about these stock markets and this kind of commodities is that there is also a forecast in the current price. So, for example, when you have a knowledge that, okay, now the demand for lithium will increase. Yeah, but that is somehow implemented to the price. Now, obviously, the thing is that, is it correctly implemented? Is it underestimated or overestimated? But it is for sure that the buyers and the sellers know that there will be increase in demand of lithium. So when somebody tells you that, for example, now I am certain that within 2 years the price of zinc will increase significantly. So you may ask that, okay, why don't you then put all your money and buy zinc and loan as much as you can? Then you'll be very rich man or a woman. The future forecasts, especially the things that are like commonly known, are implemented to the prices already, for especially to the metals that are exchanged a lot. But okay, let's go on. I discussed quite a lot about this. Well, it's a relevant thing, but not perhaps the most relevant thing in the lecture. Okay, one important critical metal or critical metals group are the rare earth elements. Their criticality is based on their use in permanent magnets that are, on the other hand, used in electric engines, for example, or wind turbines. And now this is a very typical story for a critical metal that now in this case China dominates the markets with over 90% share, and that makes it difficult for the Western world and for the Europe also. There are not much primary resources, and the value chain from mining until pure metals is not solid. But anyways, some of them are more valuable than the others. Their prices range a lot. They are a group of 17 chemically very similar elements, and this makes it interesting from a separation science point of view. So I often call it the king of separation problems in hydrometallurgy, if we try to separate these 17 very similar elements from each other. That is very resource intense, and most of the price of the rare earth comes from the separation process. And the one important fact to note about when we want to make high-tech metals or metals used in high-tech applications, we need to have very pure metals. So that makes a certain demands for the separation processes that we use. We will have a look at them later, but we need to purify very strongly, up to 99.5 typically, or even more, 99.9 or 4/9. All right, here again a little bit more about the philosophy. So when we ask, when we know that there is criticality in the metals, and we could easen the criticality, for example, in Europe by recycling more, so why don't we just do so? So let's go and collect the used electronics and circulate the metals from them. Well, yeah, but in real life it is not so simple. So actually, from the chemical engineering and from technology point of view, it's not so difficult, or at least it's not probably the bottleneck that we couldn't separate some metal from some waste raw material. So our wise, my mentor, like a PhD supervisor, Professor Erkki Paatero, gave a lecture in an international solvent extraction conference where he stated that his lessons also from industrial work was that this applies to all of the separation processes, not only solvent extraction. So you can separate practically any metal from any raw material. That's not a problem. But in reality, there are lots of other factors come to a play. So I wouldn't want to be like sort of let's say it would be modern soft talk to discuss about environmental aspects, for example. That's often done, but But to be honest, like probably the most important factor is the money. So when somebody gets a profit out of the recycling, that company will do it. That's for sure. So if it's profitable enough, they will do it. So it's not just that we couldn't separate, but we should do it economically efficiently. Then obviously nowadays it's understood well, and it's not unimportant. It's a very relevant and important thing, so that we do it environmentally and societally and socially sustainable manner. So these are sort of a boundary conditions that then countries and politicians need to set up. So we do not want to nature and environment to be ruined by our recycling or primary mining operations and the metallurgical industry. And we want to make it sustainably from a people's point of view. That's how it should go in a modern world, and very good. So we need to respect these human aspects also. Obviously, politics is an important discussion. So you may already see from the critical raw materials for the EU list and discussion that there is a political dimension strongly involved when we discuss about making quotas and whether China wants to use, for example, rare earths as a political tool or so on. So unfortunately for us, it is so that there is that dimension strongly involved. But anyways, this a little bit a few words more about the economical aspect. So I and we in the circular sustainable circularity of inorganic raw material or inorganic materials platform, we want to think it so that we want to make socially and environmentally sustainable processes and technologies, and we want to design the value chain so that they would be profitable market-wise, and that will then drive the circularity forwards. So we don't want to think so that, okay, well, now this and this country and EU and they should just tell us that now you have to recycle, but we want to think in a little bit more liberal way, so that we want to create the business. That's not a bad thing. We see here, if somebody gets business out of recycling, it will be a good thing for the whole world and for the nature also, when we don't need to dump, for example, slugs and wastes. Okay, that was the quite a long discussion about the societal background. Now we will go to the raw materials and discuss about the secondary raw materials and the ones capable of being raw materials for circular metals production, and then we will go also in the end to the separation methods. But here is my division of hydrometallurgical or metallurgical raw materials to primary ones that come from the mines, and then to the secondary ones, which contain then also the side streams and wastes from the mining industry and metallurgical industry. Sometimes this is seen to be a primary raw material, but that's just a definition. But anyways, it's a very important source of metals. They are voluminous quite often. And then there are the anthropogenic waste coming from cities and societies. So mostly, clearly the most important category here are the electronic wastes. And we will have a closer look on all of these raw materials now and give some examples. Here are some pictures. The upper left one is from a small town in eastern Finland called Siilinjärvi. The Finnish people may see this white large pile when they are driving to a famous Tahko ski resort in Finland, and the road goes by this town, and there the big phosphogypsum piles are. So it's a gypsum calcium sulfate byproduct from fertilizer industry, and these piles are located all around Europe and all around the world. And they contain interesting amount of rare earths, not so much as the primary rare earth ores, but in such extent that it's very interesting and perhaps even nowadays close to being a profitable process to recover these. And if it will be a profitable at some point, it will be a big change to the whole rare earth markets in the world, because these piles are huge and there are lots of those. Here is a picture of zinc plant residue, so electrowinning sludge or slag. It contains quite a lot of manganese, so half of the weight is manganese, and it's an important, not very expensive battery metal, but important battery metal still, used in lithium-ion batteries. Indium, critical indium, may be recovered, for example, from, and its main use is in LCD panels. A thin layer of transparent indium tin oxide is as an electrode on the surface of the LCD glass, and it contains a significant amount of indium to be recovered. And now here is nowadays the hottest topic for the recycling, so lithium-ion batteries. So the batteries contain a very large share of metals, and for example, the average electric vehicle battery then weighs like let's say 200 or 300 kilograms. So now we are seeing why it is so important topic, this battery metals and battery recycling. So it's not just, obviously it's a large amount when we collect all the small devices, mobile phones batteries and laptop batteries. It's a significant volume, but still when we consider that it doesn't weigh so much, the mobile phone battery, compared to the 300 kilograms in electric vehicle, and that's what is seen to be a very essential and big change in the batteries and battery metal markets when we are driving electric vehicles in the future. But anyways, when we pre-treat these used batteries with mechanical and pyrometallurgical processes, we will get this so-called black mass, and it contains mostly metals, and then as an impurity some organic compounds, for example. But anyways, at the best it might contain even 50% of cobalt, or tens of percentages of different battery metals. Typically, like over half of the content of the black mass is metals. Here are some solid wastes from a metallurgical industry. So this picture we already had. So here we are doing leaching for the manganese rich zinc plant residue in our laboratories. They may also contain silver, indium, germanium. Copper plant residues, when there are two main routes for copper copper manufacturing. So the hydrometallurgical route, which is like 25% of the produced copper, and the pyrometallurgical route, which is in majority. And in the pyrometallurgical route, when we are doing the electro-refining, so electrolytic purification of the casted anodes, the impurities that are there in the copper are mostly precious metals, gold and silver, and also platinum group metals. And these kind of copper plants then also quite often have precious metals refineries. Copper smelter slags may contain other base metals, also zinc, cobalt, even molybdenum at some cases. But anyways, for example, it then may be interesting. It depends on the geographical area where we are at, but very often it contains gallium, and most of the gallium, it's in the critical metals list also, or critical raw materials list of EU, and most of the gallium in the world is produced from this red mud. Then it may contain a rare earth with interesting amounts, and some other metals like titanium. We remember that now one of the new critical raw materials was titanium in the list, and red mud contains that one. A little bit underutilized this red mud, still perhaps an interesting because it's very voluminous. Aluminium is a largely produced metal. Okay, then there might be some liquid side streams, for example, in hydrometallurgical industry. Some interesting metals there might be, for example, precious metals like silver, gold sometimes, platinum group metals, germanium in cobalt plants, for example, zinc plants also. This was also a critical metal. Rhenium, which I already discussed a little bit about. So it's produced as a byproduct in copper smelters often. So copper ores sometimes in some geographical areas contain rhenium, and it ends up in a flue gas, and from there, when that gas is washed, it will create a solution where there is a significant amounts of rhenium, quite often also molybdenum, arsenic, which is also abundant in the copper minerals, and from there rhenium can be recovered. Then anthropogenic wastes, so this WEEE, waste electrical and electronic equipment. Here are some numbers. So they are generated at a rate of approximately 10 million tons a year. The amount of sold electronics is not changing a lot during, for example, last 10 years, but the collection rate in EU, it's over 40%, and a little bit less is reused or recycled than collected. But recycling rates of individual metals, they are not listed very often. The last good review was already 10 years ago, but you see that the recycling rates of individual metals, they vary a lot. So they might be practically non-recycled, and the things with rare earths and indium, they are not probably much better nowadays either. But some of the base metals, for example, are recovered up to 90% or recycled, and typically over half of the metals are recycled of the base metals. Here are some examples. So as I already introduced, the LCD screens that have the electrode from indium tin oxide, then printed circuit boards, they're copper and because it is a lot, and gold are the main metals to be recovered, also PGMs and silver. Lithium-ion batteries are discussed later in a bit more detail, and fluorescent lamps contain lots of rare earth oxides, for example, as their phosphor material, luminescent material. Okay, then we go to the processing and the recovery methods. And here is a comparison of pyrometallurgy and hydrometallurgy. So pyrometallurgy means those high temperature, let's say conventional metallurgical processes when we have smelters and so on. And then we have the hydrometallurgical methods in which we leach the raw materials and metals from them to the acids and go from there. Processing of complex and low-grade materials is better with hydrometallurgy. So there is more flexibility and selectivity because we anyways want to produce pure metals. So we quite often need to go to hydrometallurgy at some point of our process. Some emissions like gases and energy consumption are lower in hydrometallurgy. So this is seen as a growing way of metals production and processing. Here are some examples of the recycling plants. So there are pyrometallurgical ones, hydrometallurgical ones, combined ones. And one thing to note is that, for example, the pyrometallurgical plants cannot quite often produce pure metals, but they produce like a mixture of metals or concentrates, and which then need to be refined with hydrometallurgy at some other plant then. But yeah, Umicore is a large mainly cobalt concentrated company, but it has Europe's largest and perhaps most modern recycling plant in Belgium, which can then recover like almost 20 elements, critical metals also as a pure. Okay, then the lithium-ion battery waste and its processing. So really, as I already introduced, it contains a lot of metals, and for example, lithium is there as an important, and cobalt is perhaps the most interesting metal to be recovered there, and nickel also. But this is how the process usually goes. So we leach the raw material with typically sulfuric acid, add some reductants like hydrogen peroxide, and then we end up having majority of the metals in the solution. So we have a mixture of these metals. Manganese might be there also. It's not shown in the process sheet here, but nowadays at least it's quite often there. We first remove the so-called impurities by solvent extraction. We may precipitate the iron, aluminium out from there, take the manganese and copper out, for example, by solvent extraction. So we try to create a pure mixture of this most valuable battery metals here, so cobalt, nickel, and lithium. And then we will have additional purification step in which we fractionate the pure battery metals. So for example, in this publication that we had a couple of years ago, we did it with the solvent extraction process that yields then all the most important battery metals with over 99.5% purity. This is like a conventional, let's say, straightforward recycling scheme. Obviously, there are lots of variations and lots of research that has been done and is being done in this lithium-ion battery recycling topic, and very many options are available. And now probably the tough thing is to decide that which one is most optimal for which company and which country and which region and so on. It depends also what is available. So if we have a metallurgical plants at somewhere, it might be wise to, for example, create such a mixture that can be fed to that process, already existing process, and not to build a new one. So it's very complicated. It's not just about what's the most efficient process to create the most pure metals, but lots of other factors also involved there. This already was discussed earlier. Sorry that there is some Finnish, but there are other pictures in this lecture slides also. So indium tin oxide film on the surface of the LCD glass, and here we again make the mechanical milling to create sort of a sand or dust of the glass that it contains then some indium with significant amount from 100 to typically 300 ppms. Then we do just a normal atmospheric sulfuric acid leaching. We get almost all of the indium leached and some impurity metals here. And then we do the hardcore selective separation thing, which is not the most cheapest one, but very efficient here. For example, with our solvent extraction, we get a pure indium metal containing stream from which we can then precipitate or cementate the pure indium metal. Okay, but here is an interesting philosophical opening and a little bit to think about to the whole society. So should we collect our waste electronics and ship them to some place to have a very large metallurgical plant for recycling there, or should we do it like here our Italian colleagues suggest, so that we would build a metallurgical process to containers which are then transported to a smaller raw material piles. So a local recycling with the relocatable plant. That's an interesting philosophical question, because it has been calculated that definitely you can understand that it's cheaper to transport this kind of container than to transport all the waste electronics to the plant. And it's obviously environmental friendly, so less CO2 emissions when this plant is removed and relocated. But there is a prototype available also with these Italian people. Okay, but now the rest 5 minutes of my lecture I will discuss now, because we have been discussing now this hydrometallurgy and metallurgical aspects and raw materials of the metals recycling. So now I use a few minutes to explain you a little bit. So what's the trick there with these selective separation methods that can be used now in the metals recycling efficiently to make a very pure metal. So here is the solvent extraction that I mentioned already. So we have two liquid phases. So this bottom phase is our feed solution, the aqueous solution usually containing some mineral acid, typically sulfuric acid, and there are the metals dissolved. And now we use as our working horse, which is not spent in the reactions and in the process, we use so-called organic phase, which is mostly kerosene type diluent. So we may use industrial kerosene here So it's the majority of the volume. And then we have our trick, the specific chemistry there. Typically like 20 volume%, for example, is our selective separation chemical. And what is so special about it? So here I have described perhaps the most important solvent extraction application industrially, which is the copper refining. And here you can see that we have a copper and iron in the solution. So the iron is the impurity, and our magic chemistry works so that it goes to the surface of the organic and aqueous phase. Here you see it in a separation funnel. For those of you that know chemical engineering, this might be familiar from the basic labs. So in the boundary, our magic chemistry goes, and it takes only copper from here. So it goes to the surface and sort of grabs the copper metal ions from the aqueous phase to the organic phase, but it doesn't take iron. So it's selective. And that's how we purify the metals with solvent extraction. So now our copper is in the organic phase and iron is in the aqueous phase, and we might just take the organic phase out of the separatory funnel, and that's how the separation has taken place. I won't go through with this. Here are some more details about this chemistry. I think we want to move on at this point. For those that are interested, may have a look on this later. But then for the purpose, the description of my ion exchange slide is almost analogous. And it wants to highlight the fact that in principle, these separation techniques are the same, but now our working horse, our separation material is a solid plastic resin polymer. So a diameter of, let's say, 1 millimeter for these small spherical particles. And now our magic chemistry is implemented in this solid separation material. And now again, this is a hypothetical case, but for purpose, I have wanted to use the same metals here as an example. So now our solid ion exchanger that contains the magic chemistry is capable of taking, in this case, only copper and leaving iron out of here. And now we have collected to our target metal to these resin particles. So that's the principle of ion exchange. And here is another slide about the ion exchange, and now we are doing the separation chromatographically. So the basis of this separation is that we have different affinities of the metals to the separation material. So our separation material, the resin, wants to take some metal and doesn't want to take another metal. Here we do it so in the chromatography that none of the metals is attached actually to the resin totally, but it's just temporarily attached so that it is moving slower when it has the interactions with the materials and with the metals and the ion exchanger. And here is the example of crushed permanent magnet waste. So it contains significant amount of cobalt, but then most importantly, the valuable rare earths, neodymium and dysprosium. And in this case, these metals have just a little bit different affinities to the our ion exchange material, and this is what happens when we let this kind of leaching solution of containing acid and these metals flow through this ion exchange column that has been pictured also here. So this is from our laboratories, and this is what happens when we let it flow through. So we see that these metals are migrated to the column with different velocities. So this dysprosium, it has the strongest interaction with the separation material, neodymium the second strongest, and the cobalt the weakest. Cobalt then is capable of traveling the fastest, so it comes first out of the column. So now we collect the cobalt, neodymium, and now and in the end of the process we collect this process. So this was now the demonstration of the ion exchange chromatography principle. And here was now the summary, short summary and introduction for the chemistry and chemical engineering of these separation methods and the effective ones that may be used when we want to get the very pure metals in recycling of anthropogenic or mining in metallurgical industry wastes to gain metal circularity. So these were all of my slides. I want to thank you all for the attention.